I'm Mateo Johnson, and my ISEF 2025 project was on gyroscopic rocket stabilization using thrust vectored control. Traditional fin-based stabilization systems come with several significant drawbacks. When deployed at height, they often struggle with accuracy. They also present challenges in terms of cost, physical footprint, and overall precision. The fins themselves create additional drag on the system, requiring complex aerodynamic calculations to compensate. And unfortunately, once installed, these fins cannot be easily adjusted to optimize performance as conditions change. These limitations prompted me to explore alternative approaches to stabilization. My project set out to develop a thrust vector control, or TVC, system that addresses the limitations of traditional approaches. I focused on creating a solution that is simple, low cost, and compact. A key design goal was to incorporate modular hardware slots for flexibility and customization. The system needed to reliably maintain orientation and successfully follow predetermined trajectories. Additionally, I faced the practical constraint of fitting the entire system within a 2.71-inch model rocket tube, which presented interesting engineering challenges that I will elaborate on shortly. I began with paper drafting, followed by a thorough thrust analysis on the C6 engine, using Desmos and Python to estimate the thrust curve and Fusion 360 to identify critical load-bearing points. My initial design turned out larger than expected, but through several iterations of redesign, I successfully reduced the diameter to meet my target of less than 2.71 inches. On the sides of the gimbal, I mounted rods with swappable plates. This design choice allows for the versatile attachment of various components and sensors, supporting the modularity requirement I established at the beginning of the project. I printed this system using PETG filament with 60% infill density, which my testing determined to be the optimal balance for performance as shown in the figure. PETG was selected not only because of its heat resistance and weight, but because of the durability and strength of the pieces. To ensure consistency and ease of assembly, I standardized all hardware components within the system to M3. This standardization simplifies maintenance and any future modifications to the system. For assembly, I mounted the XY and servo gimbals together to create an integrated unit. I then subjected the final system to rigorous thrust stand testing to verify its responses under realistic conditions. I conducted more than 30 simulated launch conditions, achieving a success rate above 90%. Notably, approximately 8% of the failures were attributable to user error rather than system deficiencies. Through this comprehensive testing, I measured key performance metrics including response time, which was approximately 18 milliseconds, and angular deviation of plus minus 1.086 degrees. This confirmed that the system met its design requirements. After comprehensive evaluation processes, I selected the XIAO SAMD21 as my microcontroller of choice. To accurately measure the acceleration and rotation of the engine, I incorporated an MPU 6050 IMU sensor. For actuation, I chose two Tower Pro MG90S servos, which provided the necessary torque and response speed within the size constraints. One of the most significant limitations in my original design was the breadboard, measuring 165 by 55 millimeters. To address this, I first migrated the electronics to a smaller, soldered prototype board. Eventually, I developed a custom-made PCB measuring just 39 by 35 millimeters, drastically reducing the footprint while maintaining full functionality. For this project, I created a proprietary dual-mode control system that adapts to different flight conditions. My system employs recovery mode to rapidly correct large deviations, though with some trade-off in precision. When closer to a set point, the system transitions to stabilize mode, where I prioritize fuel conservation and efficiency of motion. This dynamic reaction capability significantly enhances overall performance. Additionally, my software supports pre-uploaded set points and enables the system to track spline paths for complex and interesting trajectories. In the latest versions, which have not yet been flight tested, I've implemented a neural network-based dual-mode control, which promises even more responsive and adaptive control capabilities. My simulated angular deviation measurements of approximately plus or minus 1.086 showed acceptable variance when compared to the simulated predictions of around plus or minus 0.9 degrees for the first 4 milliseconds. After this initial period, I observed the system stabilizing to approximately plus or minus 0.93 degrees, demonstrating effective dampening behavior in my PID control. I've identified two specific approaches to improve these results further. First, by adjusting the digital low-pass filter settings on the IMU, and second, by upgrading to higher performance servo motors. These modifications would further enhance the precision of the entire system, although the first one would take significant amounts of time, and the second one would cost significantly more than the project does currently. My best case system response time of approximately 18 to 19 milliseconds nearly matched the simulated value of about 17.98 milliseconds. This close correlation between my theoretical and actual performance validates my design approach. This excellent response time was significantly influenced by my implementation of the dual-mode control system. Beyond just improving response times, this control architecture effectively balanced power consumption with stabilization performance, addressing multiple design objectives simultaneously. My analysis of the control mode performance revealed distinct operational characteristics. During recovery mode, the system experienced relatively high angular deviations of approximately 2.8 degrees while requiring increased power consumption of around 220 milliwatts. As the system transitioned to stabilized mode, I observed the angular deviation dropping significantly to approximately 1.2 degrees, while power consumption decreased to roughly 185 milliwatts. This data strongly supports the effectiveness of my dual-mode control approach, and it even suggests potential benefits of a threefold control system. It provides clear visualization of how the system conserves computing resources and battery power. The intersection point of both modes occurs at 25 seconds, where both modes achieve similar deviations of approximately 1.0 degrees. The power consumption curve follows the expected pattern, peaking during intensive operations and gradually settling to a lower baseline during stability. The small differences in angular deviation and response time compared to the theoretical values, combined with my achievement of an 80% reduction in price point, clearly indicate successful accomplishment of my project goals. From a programming perspective, the excellent performance of my dual-mode control system provides further evidence of success, and my implementation successfully enables several critical capabilities: inputting coordinates relative to the rocket, uploading new PID models, controlling orientation, and holding specific angles. These technical achievements collectively demonstrate that I've met or exceeded all of the key objectives established at the outset of this project. Looking forward, I've identified 3 key areas for future development. First, enhancing the system with Z-axis or roll stabilization would complement the current XY stabilization. It would result in cleaner, more reliable data collection, and it would allow for an onboard camera feed. Secondly, I see an opportunity to implement dynamic infill based on the C6 stress point analysis. By strategically varying the infill density, I could further optimize the weight-to-strength ratio, producing lighter yet stronger components. Finally, I'm exploring the integration of actuated fins to work in tandem with the thrust vector-controlled system. This hybrid approach would provide optimal control at various speeds while maintaining stability throughout the flight envelope, combining the best aspects of both stabilization methods. My current implementation of a neural network control operates on a straightforward principle. It takes current XY positions and target XY positions as inputs, and then outputs the necessary motor values to navigate between these points. Looking ahead, I intend to develop a more sophisticated version, capable of actively adjusting control strategies in real time. This approach would not only address the limitations I observed during initial testing, but also enable on-the-fly customization of parameters and behaviors. The future neural network will be a custom-designed recurrent neural network, or RNN, with expanded inputs including target and current XY coordinates, angular velocity, estimated fuel mass, battery voltage, and environmental variables such as pressure and temperature. I plan to train this network on a combination of real and simulated flight data, with primary improvements focused on adaptive responses to changing flight conditions and trajectory correction. The main challenge with this implementation will be managing the increased computational and programming complexity. My dual-mode control system with recovery and stabilized modes represents a significant innovation in this field. The dynamic switching between modes, balancing high power and quick correction against efficiency and precision, creates an adaptive, responsive control architecture. During testing, I discovered that variations in fuel mass throughout the flight caused inconsistent behaviors. This led me to develop a rate of change function and custom adaptive PID controller that responds dynamically to changing conditions based on data responses. This modular hardware design incorporates several practical innovations: swappable plates and flexible component mounting, a web interface for easy configuration, and magnetic connectors between segments that facilitate quick transfers without risking entanglement. These design elements significantly enhance the system's versatility and user-friendliness. In conclusion, my project has successfully demonstrated that gyroscopic thrust vector-based control represents a viable alternative to traditional fin-based control systems. Through multiple iterations, I've proven the system to be robust and capable of reliably achieving its goals, with deviation remaining in reasonable tolerances for practical applications. Notably, the system achieves superior performance at high altitudes, where traditional fin-based systems lose effectiveness due to the decreasing air density. This work has opened several promising avenues for further investigation, particularly in the realm of material science, such as mixed material fabrication and dynamic infill. The system also presents opportunities for future integration, including autonomous trajectory optimization based on flight conditions, and the development of hybrid systems that combine both gyroscopic and fin stabilization. The dual-mode control system I've developed has applications extending far beyond amateur rocketry, reaching into fields such as drone stabilization and robotic joint control, where power consumption must be perfectly balanced with operational efficiency. Thank you for your time.